Hello, my name is Prateek Akula, and today I'll be talking about slicing-aided hyper inference for long-range aircraft detection. Long-range aircraft detection is the first step for enabling detect and avoid, also known as DAA. When flying in an airspace, mid-air collisions are a prominent risk to both manned and unmanned aerial systems. Failure to detect aircraft or other aerial objects could lead to high-risk scenarios with potential for loss of substantial amounts of money and even human life. Thus, it is crucial to have DAA for the safety of aviation systems. Detecting distant aerial objects is challenging, however, due to the low signal-to-noise ratio in high-resolution images. When an object is far away, it takes up a low feature space in pixels compared to the whole image. And because of that, it can be very hard to spot. In addition, when common practices like downsampling an image to feed into a network is unfeasible, because when you downsample the image, we might lose important features of the object, or we might even lose the object itself as a result of the downsampling. Because of this, we need to have a framework that can process high-resolution images. Related work to this is AirTrack and Slicing-Aided Hyper Inference, also known as SAHI. AirTrack is an object detection and tracking framework that consists of several processes, but we are interested in the frame alignment and the detection. In the frame alignment stage, we have two successive frames, which are aligned such that the eagle motion of the camera is negligible. In other words, we're able to differentiate between the foreground objects and the background. This is important because the background in these scenarios are often very cluttered, especially when you get below the horizon, when you have a lot of things in the way, like trees and other objects that make it hard for the detector to see the actual aircraft. In addition to this, the detector that we use employs an HRNet backbone. And this is important because this backbone employs high and low level convolutional feature maps in parallel. This is important because by doing so, we're able to capture unique features on the high dimensional feature space, in addition to retaining relevant low level context, which makes it perfect for our needs. In addition, we also have the slicing-aided hyper inference model, also known as SAHI. This is an inference technique in which we enhance the accuracy of small object detection by running inferences on image slices, which are then stitched back together for the whole image. For example, we can see the full frame inference right here, which is standard inferencing. The inference is run on the whole images by itself, but because of that, we might miss the small little helicopter sitting in the top right here. In contrast, SAHI will split it up into different slices and then treat each slice as its own full frame inference. Because of that, as we can see here, it takes this slice as well and expands it to a full frame, and then we run inference on that. And through this process, it is evidently much easier to spot the aircraft and detect it. In this project, I used a YOLO V8 detector backbone for SAHI. The cool thing about SAHI is that it can be applied on many different detectors. The main work of SAHI is to actually just split the frame up into slices, which then uses the backbone detector to run the inferences on each slice. So that is our model. And that was when we use these in parallel to get as many detections as possible, these are the results that we got. We have this first result right here. It's like qualitative analysis. And as we can see, it can pick up the small aircraft sitting in the distance over here, and it's able to correctly crop it out and identify it. It also picks up the aircraft that is mounted on. But we can also see here that it picks up a false positive in the background here, which is below the horizon, and there's a lot of clutter. So when you slice things up and blow them into a full image, it is easy for a model to get confused on if it's an aircraft or not. In addition, we also have another qualitative result pulled from our results to show the capabilities of our system. Here we can see that this very tiny object in the distance, sorry for that, is able to be picked up by their detector. However, it also detects two false positives in the background due to the clutter again. In the future, the next step is to interface SAHI directly with the HRNet detector from AirTrack. As I mentioned, currently we use a YOLO V8 because of its speed and its accuracy as the base inferencing for the SAHI model. This means that when AirTrack fails, the SAHI also takes over, and then due to the slices, we were able to capture these small objects in the slices. However, if in the backbone detection, we will use the HRNet detector, it'll make the detections 1,000 times a lot more positive in the detection. It also will help with false positives. So this will make instead of using in parallel, if we combine them, we'll get all the benefits and also reduce the shortcoming of false positives. In addition, after doing that, we will add support for multi-frame temporal slicing using SAHI. And by doing so, we can much easily see how an object moves over time. And then through that, be able to better detect objects with higher confidence rates. Thank you so much to the RISC program for hosting this, and to Dr. John Dolan and Rachel Burson for having us this summer. I also want to extend my thanks to the Air Lab, specifically my mentors, Nicole Keita and Professor Sebastian Scherer. Thank you so much.